Gettysburg Seminary presents the Seminary Explores podcast. Conversations on faith, art, people, politics, theology, life, and more, with voices from around the corner and around the globe.
Hello and welcome to the Seminary Explores podcast. This is Kristen Johnston-Largen, and I am here again with my guest, Dr. Craig Foltz, astrophysicist. Craig, it's delightful to have you with us again.
It's so nice to be back.
Well, I want to open our time with a shout out to my student Chris Schaefer, who said right the day that our first podcast was published, came out. I was walking from chapel, and he was across the street, and he said, "Dr. Largen, I'm so mad at you." And I said, "What could possibly be wrong, Chris?" And he said, "Your podcast with Dr. Foltz, it was so interesting, but you promised you would get to dark matter, and you didn't." So I said, "Hey, I can have Craig back, and we can start by talking about dark matter."
We had such fun.
We did have such fun. So I'm delighted to be able to talk with you again. Yeah.
Okay, we really... dark matter is an issue that came up almost 100 years ago.
Okay.
Although it was considered to be, sort of the position of an iconoclast. And in fact, it was a Swiss astronomer who was at Caltech named Fritz Zwicky, who has all... I love this description of him, that Zwicky was unconstrained by humility.
Oh, that could fit a lot of people, couldn't it?
It could. I know those people.
And I love some of them, really.
He was so far ahead of his time, and he actually predicted the existence of black holes. This is the 1930s. Remember, this is only 8 or 10 years after the realization by Hubble that these fuzzy little patches in the sky that we saw were actually external galaxies like the Milky Way.
Wow.
And Zwicky, who was a theorist, looked at the data that was being collected on the motions of these galaxies. And what you can do is you can measure how fast they're moving towards you or away from you.
Okay.
They're so far away from you will never see them move transversely.
Okay.
But using the Doppler effect, which is the way the cop gets your speed on the side of the road, right?
Okay.
You can measure the speed. And he looked at clusters of galaxies. Now, these are clusters of 100, 1,000, 10,000 galaxies like our own, each of which has billions and hundreds of billions of stars. And given the fact that now the Big Bang was getting established and there was an age estimate for the age of the universe, he said, given how fast these galaxies are moving, they should not be clustered. They should have
gone
evaporated.
Apart. Oh, okay.
And they look, what a physicist would call, they look relaxed, which means... Now, come on.
That's a scientific term, relax.
It is. What it means is the motions are in equilibrium with their gravity.
Okay.
So it's like a swarm of bees.
Okay.
They're moving around, but they're sort of held together by their mutual gravity.
And that's relaxed.
It's relaxed.
Very interesting.
So there's actually a more formal mathematical description, but it means the distribution. No,
I like that actually. Yeah, right.
The distribution of velocities is characterized essentially by one parameter, temperature or mass.
All right.
And he said, and I can look at the number of galaxies, and I can figure out how many stars are there and estimate what the total mass is in those galaxies, and how much gravity there should be.
Okay. And
then I can ask the question, is there enough gravity to hold these clusters together, given how fast the galaxies are moving?
Okay. I understand that.
Okay, you got it?
I got it.
They're moving. They seem to be moving too fast for the amount of mass that you could account for in visible matter.
Okay.
Okay? Or an estimate of that, some matter that you don't see, neutral, dust, things like that.
Okay.
And he came up way short.
Okay.
And he said, there's something else there.
There's something else there.
And astronomers said, no. Because we know everything. Right?
Of course you do.
And so, run the clock forward maybe 3-4 decades.
Did he call it dark matter, or did he
just
say something else is there?
I don't know whether he called it dark matter. He actually did postulate the existence of black holes, and I don't think he called them black holes, but collapsed objects.
Okay.
But you run the clock forward to the 70s. A wonderful astronomer, Vera Rubin, who was at Carnegie Observatory out of Washington. She's still in the field. She really is fabulous. Sort of broke the... astronomy has had women participants in research for a long time. Vera was one of the first female superstars. Right?
Wow, that's great.
And she's just a lovely person. She started to look at individual galaxies.
Okay.
And looking at the orbits of stars
in an individual galaxy.
Around an individual galaxy like our own.
Okay.
So for a flattened galaxy like ours, which looks like a dinner plate, stars are going around. In fact, there's a galactic year. It's 250 million years. So 250 million years, the sun
You're
goes...
You're thinking really big numbers.
It's big numbers. Actually, it's really tiny.
Well, yeah, right.
So think about this. The sun is the major mass in our solar system, and the planets are orbiting around it. The further out you go, according to Kepler's laws, obviously the longer it takes for them to orbit, but actually the slower the planets are moving.
Okay.
So as you take objects that are further and further away from this central mass, they should be moving slower.
Okay.
And so Dr. Rubin was looking at the velocities of stars way outside, on the edges of the galaxy.
Okay.
And she found that, in fact, the speed with which they were orbiting did not drop off.
Oh.
It stayed high. It
Okay.
stayed flat.
Okay.
So astronomers would talk about flat rotation curves, which was if you're drawing a graph of the rotation speed of the stars as you move out from the center, it should go out, sort of rise and then go down because the mass is not fully centrally concentrated. But Rubin found that it stayed up high, and she said there's something else there.
Okay.
And in fact, what we realize now, and there's a lot of argument that goes into this, and there's a lot of evidence for this, is that there is a component of the mass energy budget of the universe, right? Mass and energy are the same.
Okay.
E equals mc squared, right? So you can take all the energy in starlight and the microwave background and express it as a mass.
Okay.
Only about 6% of that is normal matter. So, and there is another component, and we see its effect.
That's 94%.
Now, there's two other components actually. There's the dark energy, which is about. Let me see if I can get my math right. About 26%.
Okay, dark energy
is dark matter.
Okay.
And around 69% is this newly discovered thing that we really don't understand called dark energy.
Wow.
So the stuff that we're all made of is a trace of the universe.
Okay.
And we see the dark matter, we see its impact in the light of more distant objects. Okay, because matter deforms space,
yes,
which is really an issue for LIGO.
Yes.
Because it deforms space, it can act essentially as a lens.
Okay.
A big concentration of matter.
Okay.
A galaxy or a cluster of galaxies or a big blob of dark matter can cause light rays from sources behind it to deflect.
Okay, sure.
And in fact, they will create these. There are beautiful pictures of galaxies that are distorted by these so-called gravitational lenses.
Okay.
And you can, from the geometry of the lens, you can calculate what the mass is of the deflector.
Okay.
And it's not baryons. I mean, think about us as baryons.
Yeah.
Regular stuff. And don't worry about the photons and stuff. But normal matter, and then which is baryonic.
Okay.
And then there's the non-baryonic dark matter.
Okay.
And
dark because you can only see its effects, but you can't see it.
Exactly. And we talk about it as cold dark matter.
Is it cold?
It's that has its own meaning too.
Okay.
kind of like relaxed.
Okay.
All right. It's dark because it only interacts gravitationally.
All right.
It doesn't collide with matter. It doesn't emit light. It doesn't absorb light. It is simply a source of gravitation.
What's the difference between dark matter and antimatter?
Antimatter is baryonic.
Oh, okay.
Okay, antimatter is a good question. And maybe we could get back to antimatter. And then I'll have to come back for
yet another podcast. Okay.
Antimatter we can create in accelerators. Antimatter is, if you take, here's the long and short of it. A hydrogen atom has a proton in its nucleus.
Yes.
A big heavy particle that's positively charged.
Yes.
And a light electron that goes around.
Yes.
Antihydrogen would have a big negatively charged particle.
So it's like the opposite.
It's the opposite in charge.
In charge. Got it.
And now when matter and antimatter combine, they annihilate one another.
Okay.
And so there's a question, and we can go back to the Big Bang again, but there's a question, why is most of the universe matter? why is there an asymmetry?
Oh,
Physicists love symmetry.
Yes, don't we all?
But
Yeah.
heaven knows. No offense.
Well, it's okay.
Heaven certainly knows. Heaven absolutely knows.
Yeah.
Why, when in the early universe, when it was enormously hot and the matter was essentially acting like light, it was fully relativistic. There were these transformations from photons to particles.
Okay.
So a very high energy photon, a very high energy bundle of light would spontaneously turn into an electron and a positron.
Oh, okay.
And then those would collide and they'd produce photons.
Okay.
So all this, there was an enormous mix. Essentially everything was acting like light. But if it was making an electron, it also had to make a positron.
Okay.
Which is symmetric.
Okay, right.
Why are we left with an overdose?
Yeah. Oh, that's interesting.
But
okay.
we don't quite know.
But Chris is saying in my ear, back to dark matter.
Back to dark matter. So we know it's there. We can see its impact. We have some wonderful. We have just sort of the smoking gun where there are two clusters of galaxies.
Okay.
Now, clusters of galaxies, again, 10,000 galaxies, and interclustered gas,
Okay.
and these two clusters have collided.
Okay.
Which they do.
Okay.
And that's not catastrophic, by the way.
All right. As long as it's not ours.
Even if it were ours.
Even if it were ours.
Yeah, they sort of pass through. The stars
Really?
pass through each other, right?
Really?
Yeah, sure. We have lots of images of colliding galaxies.
Wow.
Think about it. It's a long way between stars.
Yes.
So, we have they kind of pass by.
All right.
But in this
funny.
case,
Yeah,
you have a shock, a big gas cloud that is shocked. There's new stars forming there, which is where these two collapse, where the baryons collided. And there are two blobs of dark matter that sit outside. So basically, the dark matter just passed through because it doesn't interact.
Right.
The gas in the intercluster regions. And so you have these two gravitational lenses.
Yeah.
It's very cool. So, what is it? We have no idea.
Okay.
We have, initially there were sort of, astronomers love acronyms. And, it drives me back.
Who doesn't love a good acronym?
Well,
also, along with,
here's one of the early ones.
Okay.
It was a macho.
A macho.
A macho.
Stood
a
for?
massive, compact halo object.
All right.
And this was an early attempt to try to get around the fact that it wasn't baryons, and maybe these were dark agglomerations of matter, burned out stars, planets that never lit up, that sort of thing, in the halos of the galaxies, which would sort of merge together in the cluster.
Wow.
These were sought for, and you could set quite a good upper limit that these things don't exist.
Wow.
So the next candidate, or one of many other, there are a variety of candidates that basically come down to exotic particles, subatomic particles.
Okay.
Not baryons, so not neutrons.
Right. Not the ones
not
we know.
Yeah. So they're called WIMPs.
They go from being macho to wimps?
WIMPs, right. I think it was a reaction. It's a weakly interacting massive particle. So massive on subatomic scales, but weakly interacting because it's dark. Now, what do we mean by cold?
Yeah.
Cold means that it's not moving fast.
Oh, okay. All right.
As if it were moving fast. The way you try to constrain all these things is you take the best supercomputers you have, and you try to produce models of the universe, or a substantial slab of the universe, size of the universe, where you're gravitationally and hydrodynamically allowing particles to interact, and you're looking at the structures that are produced.
Wow.
Because our universe is full of structure.
Yeah.
It's frothy, right? It has big voids.
Frothy. Oh, I love that. Fabulous.
That's not an acronym.
Okay. Does it mean something different, or is it just like the ocean? It's frothy.
No, it's frothy.
I love that.
It's got big bubbles that are empty, big voids.
Man.
It's got concentrations, which is where the clusters are, and then there are clusters of clusters.
It's amazing.
So you see this sort of lacy structure in the universe, and if the dark matter were hot,
moving quickly.
Like a neutrino. That was another candidate early on was where they were called neutrinos, or there were hot neutrinos, which moved nearly at the speed of light.
Wow. Okay.
And there's just lots and lots of them that we can't account for. But let's call them they're low energy neutrinos. They would be described as hot dark matter, and that would tend to wash out these the froth. It would make it I'm trying to think of the best way to put this. The concentrations of matter would not be as distinct.
Oh, that's interesting.
So
we know they're not hot.
We know it's not hot.
Okay.
We know it's dark.
Not hot,
We've spent a lot of federal money trying to find. And you do it at the darndest places. You say, if we indeed have particles that are weakly interacting, they pretty much go through the Earth.
Okay.
So let's try and set up detectors.
Yeah.
And we want detectors to be in a clean environment with respect to elementary particles, with respect to cosmic rays or radioactivity, that sort of thing. So you tend to put these things in very, very deep mines.
Okay.
So you build big, and there are a number of detectors that have been built that have been put in extremely deep mines, some in South Dakota. There's a deep mine in Japan.
Okay.
And so far, there's no candidates that have been discovered.
Okay.
So dark matter remains enigmatic.
Okay.
We don't know what it is, but it's like 4 times
There's
more.
A lot of it. Right.
There's a lot of it.
Now, how does dark matter relate to dark energy?
Dark energy is...
Which I've never heard of, actually.
I'm surprised.
Okay.
A recent Nobel Prize was given to the guys who discovered it a number of years ago. Dark energy, we have to go back to the Big Bang.
Okay.
And remember, we go back to the Big Bang, we humble ourselves, we say we're in a galaxy, and we look out and all the other galaxies seem to be moving away from us.
Okay.
And we say, oh, we're special, but we're not.
Okay.
Because what we're seeing is an expansion of space. And so every galaxy is moving away from every other galaxy, more or less.
Yeah, right. Okay.
Because the fabric of space is expanding.
Okay. Mm-hmm.
Okay?
Right.
That's the Big Bang.
Yep.
Says that the Big Bang happened everywhere.
Yep.
All right? We're not in a special place. And it's a really good theory. But what it would predict is, so you have this, and dark matter or normal matter, you still have gravity.
Yeah.
So if space is expanding due to something that caused it to expand, why isn't it slowing down?
Yeah, it's still expanding.
It's still expanding.
Okay.
And there's gravity that should be slowing
it down.
And so for years and years...
And that slowing should have started...
Right away.
Yeah, right.
Right away. And you should be able to see it. And you would see it by looking at what's the expansion rate at very large distances, looking very far back in time.
Yeah, looking back in time. I love that.
It's easy.
We talked about that last time. I love that. I know.
So you look far away, you look at the expansion rate way back in time, and you see how that compares to what you would expect for no deceleration or deceleration. And for years we looked for this because the answer to that question, what was the magnitude of the deceleration, would tell us whether the universe was going to expand forever or whether it was going to subsequently collapse.
Right, yeah.
It also told us what the geometry on large scales of the universe is. That is, if you have a triangle, a spectacular triangle, big triangle, is the sum of the angles?
Oh, yeah. Okay.
Is that more or less than 180 degrees?
Sure.
And if it's more, then space has a positive spherical curvature. So we go through all these arguments.
Okay.
And in order to do it, you need to find the distance to distant galaxies. And that's really hard to do.
Okay.
It was realized in around the 80s that there was a type of supernova explosion. Okay, supernovae are these titanic stellar explosions. There was a type of explosion that all seemed to be about the same in terms of their brightness, more or less.
Okay.
And this is very good because this gives what astronomers would call a standard candle.
Oh, yes, right.
Okay. So you have something that you know the intrinsic brightness of.
Yes.
And if you know its intrinsic brightness and you can measure its apparent brightness, then you can get its distance.
Okay.
So this was really good news.
Yeah.
And lots of effort went into refining these supernovae as distance indicators to look for what other parameters do we need to really define it as a standard candle. And when there were several teams who did this, one at Berkeley, centered at Berkeley, one centered at Harvard. They were distributed. They used ground-based telescopes. They used Hubble.
Okay.
And they shared the Nobel Prize in the end.
Okay.
They started to look for supernovae at very large distances. Now the problem is with supernovae is they don't last very long.
Okay.
All right. They light up They maybe are bright for a month, and then they decay in brightness.
Oh, okay. You really mean like in real time, not long.
In real time.
Not like physics time.
No, real time.
Long time.
Now you get a little advantage because there's some time dilation.
Oh, okay.
But we won't worry about that. I mean, that's simple. That's factors of 2 or so. So this team had a very complex. These teams had a very complicated means of trying to detect supernovae. They had to detect them, and then they had to confirm that they were Type 2 supernovae, and they had to measure their recession velocity, how fast and how bright they were. Mm-hmm. And so it required very careful coordination and a lot of accommodation by the people who run the observatories.
Okay.
Because if you're scheduling a space telescope, you're not used to somebody saying, "Hey, you've got to take it tonight and point at this." Because the observing schedule for Hubble is established sort of months in advance.
Oh, I imagine.
And in fact, the observing schedule for most ground-based telescopes is established months in advance.
How long does it take to
do the
calibrate
observation?
It to a certain...
You could do... they would get a spectrum in a night. Certainly.
Oh, okay.
So they would use 4-meter telescopes on the ground to try to detect the supernovae. Then they'd use Hubble to measure the brightness and Hubble to measure the spectrum.
Okay.
And when they did... So this allowed them to go way out and say, okay, what's the distance? To get that from the supernova brightness, and then what is the expansion velocity? How fast is it moving away? And you get that from the spectrum of the galaxy if you want to, and you expect it to show that there has been a deceleration. In fact, it shows that there has been an acceleration. That the universe is not only expanding; it's speeding up.
Really?
Mm-hmm. Mm-hmm. And that does a couple of things. It says space is flat.
Okay.
You're good with standard geometry. It says that the universe will expand forever.
Okay, we're not going to collapse again.
It depends on what you like. I was kind of, I mean, it's...
Is it cold and dark or hot? And
I mean, it's rebirth, right? On one hand, you got rebirth.
Yes.
On the other hand, you've got entropy death,
That's
right?
very interesting. Okay.
Right.
Really, though, is that common now? The assumption is we're going to just keep...
Yeah, we'll go for it.
We'll go for it. Okay.
And so, but what is causing this expansion?
Right. Okay, that's the question.
And the answer is dark energy. And then the next question is, what is dark energy?
Right.
All right, there's something that's dark. Okay. There's something that you can't see.
Again, that you can't see, right.
Initially, it was called quintessence. Some people love that.
Oh, that is outstanding.
Most astronomers said, that's too many syllables.
Just call it dark.
We need something easier. We don't know what it is.
Okay.
It could be very straightforward. It could be a natural consequence of general relativity, which we love more and more every day.
Okay, yes.
It could be that the vacuum itself, this is a tough one, the vacuum itself
It's all tough, Craig. Just saying.
I should have a little beeper that says, this is a little light that lights up that says, this is when Craig gets close to the limit of his knowledge.
Right. This is when we've lost him altogether. All right, vacuum. I heard something about it.
This is the world of particle physics.
All
this
right.
is if the vacuum has a non-zero energy.
All right.
That there, and it could, because maybe in the vacuum there's a constant creation and annihilation of virtual particles that come into being along with their antiparticle, and they disappear, and they have a non-zero energy, vacuum energy.
All right.
And that's a really nice one, because as space gets bigger, the volume gets bigger.
Yeah.
The energy per volume stays the same, so the amount of dark energy would increase.
Okay.
I'm turning on the light now, which says Craig has hit the end of his knowledge. Okay.
All right.
We don't know what it is.
Okay.
It is certainly there.
Okay.
But it's the 70% of the universe.
Yeah.
So,
wow.
So if you felt small before,
oh my gosh.
So this is really kind of the outre
that's amazing
of cosmology.
Well, we've touched on it, but we haven't actually gone there. I had said to Craig before you sat down this new discovery that the New York Times reported on February 11th: gravitational waves detected, confirming Einstein's theory. And I just want to read a couple things, and then I'm going to have you explain them. So the lead paragraph is: a team of scientists announced announced on Thursday that they had heard and recorded the sound of two black holes colliding 1 billion light years away. A fleeting chirp, which apparently there was a link to in the article. I didn't link to it.
You can listen to it.
That fulfilled the last prediction of Einstein's general theory, and this is the evidence of gravitational waves. And my favorite thing in the article, it says, scientists have finally tapped into the deepest register of physical reality, where the weirdest and wildest implications of Einstein's universe become manifest. So
that's a little hyperbolic.
Oh, okay.
All right. This is
okay. Go, Craig.
Let me preface this. This is really, really big.
Okay.
This is the one that sends chills down physicists.
Really?
Yeah.
All right.
This is it.
And do we say again like what a genius he was?
No, yeah.
I mean,
well, you say
you know that or not. I mean, it's just, to me, this idea, and this is a whole other thing we're not even going to get to, but the idea that I can't see it. There's no way to sort of prove it, but my math says it's there, and so it's got to be there.
Yeah.
It's just kind of phenomenal to me.
It is remarkable.
I mean, I know you all do this all the time.
No, we don't do anything like what he did.
Okay.
This was a very, relatively elegant, simple theory.
Okay.
And it keeps working. It just keeps on giving.
Man.
Right? And so this is the one that the people who wanted to go with alternative theories of gravity. Now, general relativity is a theory of gravity.
Okay.
And we don't really want to call it gravity even, but it's a theory. Special relativity unifies mass and energy.
Okay.
General relativity brings space in.
Oh, right. Okay. Yep.
So if you think about something that is orbiting around another body, Newton says that's because there's a mutual force between them.
Okay.
It's a force.
Yes.
And we can't see that force. So why is that force any more special than dark energy, right?
Okay.
It's just because you're familiar with it. Balls drop onto the floor.
Okay.
So Newton would have said these two things attract one another. Right? Einstein said that no, the presence of mass deforms the space.
Right. Yeah.
Okay? And so it's like a rubber, the traditional analogy is a rubber sheet with a ball bearing in it.
Oh, okay, yeah.
So if you shoot BBs by it, roll them by it, they're deflected.
Yep, okay.
And they could go into orbit. It's like the thing
amazing.
At the carnival where you drop a quarter in.
Yeah, right. Yeah,
it's
right.
It's exactly like
okay.
that. Only it's a four-dimensional space.
Okay.
Space-time.
Wow,
And so, there were classical theories about did this work or not, and we would look at the precession of the orbit of Mercury, and during total eclipses, people would look at stars right by the edge of the sun and see that their light was deflected a little bit. It all worked pretty well.
Yeah.
But there were alternative theories that could be thought of. But another prediction of Einstein's theory is that if you have masses that are in motion or are colliding, and it's easy to think about this if you think about things on a rubber sheet.
Oh, sure, okay.
That if they're moving around, they're deforming that sheet.
Yeah, right.
They're sort of providing impulses into space, which his theory predicts would send waves out.
Okay.
Like deforming a sheet,
Yeah, sure.
And those would. The ramifications of those is that they would be deformations of space.
Okay.
So if, in fact, you had two test particles out in space and a gravitational wave came by, it would do this.
Okay.
Not because they're attracting one another.
Right. Yeah, right.
Just the space between them is changing its size.
Yes. Okay. I got it. I really do.
Good.
I believe it.
That's what it predicts. So how do you find it? First of all, gravity is extremely weak.
Yeah, right.
And there have been a number of tests to try to demonstrate that there was, in fact, gravitational radiation. One, a number of years ago, won a Nobel Prize. There were two pulsars going around one another, and when you orbit, you lose energy to gravitational waves, presumably. And that would change the orbit of the pulsars. And in fact, it was consistent with that. But it wasn't a direct detection of gravitational waves. So there were lots of people who tried various things, big, huge metallic bars looking for changes.
Yeah.
And in the end, there were two groups, one at MIT and one at Caltech, led by people of supreme intelligence. And unbelievable tenacity.
Yeah, unbelievable tenacity.
Tenacity.
Absolutely.
Who managed to get, and I can say this as a former employee of the National Science Foundation, managed to get a somewhat conservative agency to invest $600 million.
Yeah. The total, I mean, it was huge.
It's huge.
Yeah, it's huge. Yeah.
I mean,
it's a lot
or
of money.
in recent parlance, it was huge.
Huge.
I'm sorry. I'm about to say that what we ended up building really reinforces my feelings about the nobility of our species, that we should do such a thing. That first of all, that we should think such thoughts.
Yeah.
That we could understand this. And let me say at the outset, gravitational waves will never have an impact on you or me.
Okay.
There's no way to tap them. There's no value to them. They will give us a new view into the universe.
Yes.
And everything that we've done with the universe so far, this is why you get chills, has been because of light.
Yeah.
Now, granted, we've been to the moon. We picked up some rocks. I mean, really.
Yeah.
And you say, "Oh crap, they're just like on the Earth."
Some people are going to disagree with you about that, but anyway.
No, but they're very much like the Earth, right? And we think they came from the same body, right?
Right.
I think it's exciting.
Yes.
But that's 250,000 miles. That's all that we've sampled. Okay, you could say, well, we put things on Mars. Okay. But everything else we've learned from light. Mm-hmm. Now we have a new pair of glasses.
Yeah.
And so anyway, getting back to it, these two detectors were made. How are we doing?
We're doing fine.
And they're called LIGO, the Laser Interferometer Gravitational Observatory.
All right.
Again, they could have come up with a better acronym.
We'll go with this one, LIGO. Yep.
So they are two nearly identical facilities, one in Hanford, Washington, and one in Livingston, Louisiana.
Okay.
I don't know why they're there, other than maybe it was somebody's some influential
senator. Yeah, right.
But
okay.
they're there.
Okay.
And they were built by a consortium.
Okay.
And when this all started, there were a few gravitational physicists who were worried about such things.
That's its own separate field. I mean,
exactly. And the community is now over 1,000.
Wow.
Thousands of
Okay.
people. This is a huge activity.
Okay.
And what they are two very traditional design in principle, so-called Michelson interferometers. They are just two 4 kilometer.
Okay.
Each one has two 4 kilometer long vacuum chambers.
That just point up into the sky?
No, they just lay on the ground.
Oh, okay. Are they buried?
No.
They're
above,
you
they're
can
above
see
ground.
Them.
You can see them.
Okay.
I mean, you can't get into them.
Yeah, so I was going to say, right, okay.
And they're
I can't see them.
And this is all done with mirrors.
Okay.
And there are mirrors that are very, very held very, very delicately.
Okay.
And then there are very strong lasers.
Okay.
Okay. And these are configured in a way that the laser fires light out, which is split into two beams.
All right.
They go out to the mirrors at the end. They actually bounce around a number of times. And then they come back and are combined.
Okay.
And when they're combined, if the two waves are out of phase,
they
zero out and there's no light.
Okay.
Okay. If you move one of the mirrors a little bit, then the light will get brighter.
Okay.
The combined light will get brighter.
All right.
And this is a lot to do without a whiteboard, but
we're doing pretty well.
All right?
Okay. Yeah.
And so with this device, you can detect a change in length, a fractional change in length. Okay, a fractional change in length of the beam.
Okay.
Of 1 part in 10 to the 21st power.
All right.
All right. Let me give you an analogy for that.
Very small numbers.
It's a very small number. It's a thousandth the diameter of a proton. That we should do such a thing.
Yeah, that we should do such a thing, honestly.
I mean, just the temerity of saying.
But this sounds like it's all an experiment that's happening right here. But this implied that there was something.
Yeah, because what you're looking for is the gravitational. The only thing you're going to detect all sorts of things. Trucks.
Yeah, I can't imagine. Yeah, right. A little mouse who's. Yeah, right. Okay.
So you have to have two.
Yeah.
And you have two because you look for coincidences.
Okay.
You rule out the anti-coincidences.
Sure. Okay.
And if it's an earthquake,
Yeah. Right. Sure.
So there are thousands of different sources of metadata where they monitor temperature, they monitor seismic motion, all this sort of stuff. But what they're looking for is a gravitational wave that comes from someplace in the sky, something that happened with a lot of matter.
Okay.
Right now they're fairly crude.
Okay.
So they're looking at things like two black holes coalescing.
Right.
Specifically.
Right.
Here.
Exactly.
And that was way far away. And
Okay.
in our galaxy, you might see neutron stars coalesce.
Okay.
You might see supernovae blow up. But it's something that perturbs space.
Yes.
And so what happens is that wave comes along, hits one of the LIGO detectors.
Yes.
And they see a characteristic signature. And then a little while later, like 7 microseconds later, they see it at the other, because they move at the speed of light.
Yeah. Okay.
Okay? So
Okay.
you see the wave pass through the other one.
Okay.
And that tells you, like, somewhere on that part of the sky, something happened.
Something just happened.
And what was great about this one is what they saw was the coalescence of two black holes that were orbiting one another.
Yeah.
That's a problem that you can work pretty well in general relativity. You can predict what the waveform should look like.
Oh, okay.
All right.
Okay.
And there could be many more complex waveforms, and there are people who try to calculate them. But what it is a chirp. It's a
That's
okay. It's
a fleeting chirp.
It's a chirp. It is a low frequency wave. Then the frequency gets higher and higher.
And how does this? You talked about that it was brightness. So how does this translate into sound?
Oh, it's just you could play it. You could take the waveform.
Oh, okay,
and
yeah,
could play
it. Okay,
yeah, and it's a.
So.
It's very short. It's
Oh
very
my
short.
gosh.
If you go to it, you think
Honestly, yeah, right. Play me a little more.
Okay, let me tell you. I mean, this is so marvelous. If you think about the accuracy of these devices.
Yeah.
Okay, think about the nearest star. It's off 4 light years away, and I'm embarrassed to say I can't even tell you how many miles there are in a light year, but it's trillions.
If you made it up and said it with confidence, I would believe you.
But your listener would.
I know. That's exactly. That's exactly. He doesn't know anything, right?
So, LIGO's sensitivity, its accuracy, is equivalent to being able to measure the distance to the nearest star, 4 light years away, to an accuracy of the diameter of a human hair. This is why we get shivers. This is the one.
I know, really. Yeah, you guys are crazy.
This is the one. And there were a lot of people who said, and a lot of esteemed scientists that I know who said, they'll never see nothing. It's a waste of money.
Yeah.
It wasn't.
It wasn't.
Because even if they hadn't, there comes a time after putting it online, and it's just recently come online. It's not even all the way online, and it's in its enhanced form. Where if you didn't see anything, you could say general relativity is wrong.
Wow.
Because we don't see any gravitational waves.
Right.
And by now we should have.
We should have.
Because we look out far enough that we encompass so many galaxies that these very improbable events should have happened somewhere. Yeah. So what is the event? It's 1.3 billion light years away. So 1.3 billion years ago, 10% of the age of the universe. So really pretty recently.
Yeah.
2 30 solar mass black holes, which is an interesting one. I mean, that's the other thing. This really sort of confirms the existence of
black holes, yeah.
That were orbiting around each other, decayed because their orbits lost energy because of the gravitational waves.
Yeah, okay.
And they coalesced.
Okay.
When they coalesced, they released so much energy in gravitational radiation that they outshone, for a very brief instant, the power that they released was greater than the entire rest of the universe. Isn't it? This is why it's big. This is why it's really big.
Yeah. But this is going on all the time, right? So something in here, it talked about something like the universe was wavy, or the universe was whatever that.
The universe could be full of gravitational.
It was just that space and time are interwoven and dynamic, able to stretch, shrink, and jiggle.
Yep, that's what. So we're seeing the jiggles.
We're seeing the
just seeing the brightest of the jiggles right now. The one that you really want to go for sooner or later is to see if you can see the gravitational radiation that would have resulted from a tremendous expansion in the very, very early universe.
Okay.
With the so-called epoch of inflation, which is, again, means something different than the consumer price index.
Yeah, right.
It means in the first billionth of a trillionth of a second, the universe it grew exponentially. It doubled in size many times, very, very quickly. And this gets around a problem in a long-standing problem in cosmology, that if I look out there many tens of billions of light years and look at the universe, and I look over there in the opposite direction, the same distance, they look pretty much the same. Why? Those are not causally connected.
Yeah.
This one over here hasn't had enough time to see light or to interact with the material over here. See what I mean?
Yeah, yeah.
The universe, turns out, is homogeneous on large scales. It's very similar.
Wow.
Now, it changes with time. So but that's that was always a problem for the Big Bang. If there hadn't been some instant where it was homogeneous before, and then it inflated and took things out of causal connection. So if we could see that, if we could actually see you can imagine that this would produce gravitational radiation.
Yeah.
Not of a nature, perhaps, that LIGO can see.
Okay.
But it's a new, in the end, it's to me, it's extremely exciting. You won't, it's not like the floodgates are going to open and there's going to be hundreds of thousands of detections every year. We're still, and how much better can we get? I don't know.
Yeah. It's amazing.
But it's amazing. That's the long and short of LIGO. It's hard. I mean, again, Craig, I'm always so happy to have conversation with you because even just the little bit that I can understand and sort of process. I mean, there's a sense like we have talked about before. The magnificence of our universe, right? It's a wonderful universe. And the questing mind of humanity and what that can do and all of that. It's really quite amazing to me. It's also humbling.
Yeah,
which I think
it is
really good.
Yeah, that's exactly right. Yeah. Which is not so bad either.
Yeah, particularly in these days.
Yeah, right. Well, again, thank you so much. A delight to talk with you as always. And hope to have you back at some point.
Thanks.
You have been listening to The Seminary Explores from historic Seminary Ridge in Gettysburg, Pennsylvania, a production of Gettysburg Seminary. We invite you to visit our website at www.ltsg.edu. Opinions expressed on this program are not necessarily those of Gettysburg Seminary or the Evangelical Lutheran Church in America.